The Hille-Yoshida theorem is probably the most important theorem in this entire chapter, and in the name Hille-Yoshida there's no n missing, I'm sorry, it's really Hille-Yoshida. So this answers the question, when is an operator generator of a semigroup? So given A, when does this actually generate a semigroup? And I guess you understand the importance of the question right away, because semigroups are solutions to differential equations, right? So if you have a generator, when can you find a solution? So that's another way to phrase the question. And here is the main result. So we have an operator in Banach spaces X. This is generator of a C0 semigroup, which exponential bounds. So the norm of t is bounded by m e to the omega t. If and only if we have two conditions, dA is dense and A is closed. And for each lambda which is real and larger than omega, it is in the resolvent set, and the resolvent r lambda A to the n can be estimated by m divided by lambda minus omega to the n. So it's a norm estimate for the resolvent, which depends on the distance of lambda to the growth bound omega. Okay, so this proof is rather long and involved, so I set it down into 4 steps, where so we have to show equivalencies, right? So we go from semigroup to items 1 and 2, and then we go from items 1 and 2 back to the semigroup. First of all, if we have a semigroup, we know already that dA is dense and that A is closed. So semigroup implies item 1 just quickly. Now that also item 2 follows from a semigroup, we need to have a resolvent estimate, r lambda A to the n. And I use a very funny way to write down the resolvent, using these integrals I n lambda of x. It turns out later that I n lambda will actually be minus resolvent of A to the power of n. So far it looks more like a gamma distribution applied to t of t. So it's 1 over n minus 1 factorial, integral from 0 to infinity, t to the n minus 1, e to the minus lambda t, t of t x dt. Okay, so far so strange. So what can we do with this I thing? Let's move on here. Yeah, here I say again, I want to show these relationships here. Let me give a little box. So this is what I would like to show then in the next little while. So the inequality actually is straightforward by using the exponential bounds and integration by parts n minus 1 times. So what do I mean by this? I go back to the definition of the IN here on the previous page. And here you have we have our t. Why is it always red? I want blue. And for t, we also have this estimate. So if I take the norm of this entire thing, I can estimate the t term by m e to the omega t. And the lambda term, lambda can be complex, so the absolute value I can estimate by the real part of lambda. Okay, so that's what's happening here. In the next, so here I have, where is my pen again? Here is lambda, and here is the m and the e to the omega t. Okay, so that's the estimate I did. But now we have t to the n minus 1, so we can do integration by parts once, and then one n minus 1 cancels in the front, and we get t to the n minus 2. And we do it again and again and again, until we get something m divided by real part of lambda minus omega to the power of n. So now I want to show somehow that this IN is also a resolvent. So I apply it to A. Okay, so I apply it to A, which is happening right here. So I write the whole thing down where I put in the A right there. But I know A, t is also d by dt of t. That's the semigroup that's one of the fundamental theorem results. And then to get rid of the time derivative, I do integration by parts once again here. But now this is a product rule. I get 2 terms. Once I differentiate the t, and one where I differentiate the exponential. So then I have 2 terms, okay, from the integration by parts. But now it turns out the first term of those two is this shifted in, so it is I at n minus 1. Whereas the last one is the original in with a factor of lambda. So, which means we get a recursive relation between the in's if I apply it to ax. Let's do the same calculation for I1. So if we have a recursion, we want to start somewhere. So let's apply I1 to A. So then the t has an n minus 1. If n is 1, then we have t to the 0. So this is gone. And then we get the A here, which then becomes a time derivative d by dt of t from the fundamental theorem. Again, we do integration by parts. Now we get a boundary term at t is 0. And the other term over here, which again is I1. All right? So this is not difficult analysis. Maybe I was a little bit fast, but you can stop the video anytime and just look at it. So then we have a recursive relation from the first bit here. In times ax minus lambda x is minus in minus 1 of x. And since t and a commute, we also have the reverse direction for the same inequality, for the same equality. For I1, we get an x here. So this is the identity operator or the minus identity operator. And so then we get I1 times a minus lambda I is the identity or the negative identity. And a minus lambda I1 is also the negative identity. So I1 is the resolvent. That's what we find. We find minus I1 is the resolvent. Wow! This came from these integration by parts and recursive relations. But it's also the integral e to the minus lambda t of t. Which is, if you look around a little bit in other courses, this is the Laplace transform. So it turns out that we can write the resolvent here on the left as a Laplace transform of the semigroup. And this is a very big thing. This is a really, really cool relation. And remember, we had the semigroup triangle. So then this gives us a relation between the semigroup and the resolvent. So maybe the cow or the horse can be replaced. Yoo-hoo! All right, and then we use a recursive relation above, and then we also find that for the higher order terms, we have the exponents of the resolvent with a minus sign.